Good afternoon, everybody. Tim Lankish here from CAE Services. We're going to wait for people to filter in here, and so if you give us a couple minutes, and we'll get started at that time. Okay, just waiting for people to filter in here, so give it another minute or so. Okay, let's go ahead and get started. So welcome everybody to the latest installment of the Ask the Moldflow Expert series here, presented by CAE Services. Our topic today is windage analysis. This is something we've covered before, but I think it's an important topic for a lot of people to get to know and get to know better. You know, what do we do in the cases where we can't fix warpage? So that's what windage is all about. My name's Tim Lankish. I'm the Vice President of Research and Development here at CAE Services. My background is in physics and math. I've been here almost 30 years now, been a long time. I'm expert certified Moldflow analyst. I've trained 15 plus expert certified engineers. I've written several trade magazine articles that you can find on the web. And I've presented several times at the Moldflow Summit that Autodesk puts together from year to year. Here's my email address if you ever want to contact me with any questions that are Moldflow related. Love to hear from you. So that's a bit about me. My company, CAE Services, was established back in 1988. In our consulting work, we have the most expert certified Moldflow engineers in the world. We are also an Autodesk partner, reseller of Moldflow software. We're tasked with training, mentoring, this and so forth, everything Moldflow. We've completed something on the order of 33,000 projects over the years in our consulting work, and there's our website if you want to learn more about us. We have a technology center out in the western suburbs of Chicago, molding machines and so forth. So helps us to get the practical side of injection molding along with the theoretical when it comes to Moldflow. But that's not what we're here to talk about. We want to talk about how to fix warpage. So how do I fix the unfixable warpage is the big question in everybody's mind, right? You seemingly have gone through all the steps, done them properly. We've figured out where we want to gate. We figured out what kind of material we want. We designed our part with all the plastics 101 things in mind. You know, we've got great cooling. We've done it all. We thought we had this one in the bag, right? But then we come up with a part like this, and the thing's still warping, you know, over ½ inch. So what do we do in those cases? How do we fix something like that? And that's what we're here to talk about. So it's all about windage, or some people call it Kentucky windage. It's a process where we bias the tool steel to help reduce or eliminate the warpage. The steel is biased in the opposite direction of the expected warpage. We have to figure out how much to do it. That's called the windage factor. You know, sometimes the windage factor may be 1:1, as you see here, or in this orange shape here, it may be something less than 1, and we'll talk about those cases where maybe it would be less than 1. But we want to hit the target here in the middle. You know, so we have to figure out how much we expect it to warp before we can figure out how much windage to put in there. So why is it called Kentucky windage? You know, for all you Bugs Bunny fans out there, it comes from the Kentucky long rifle. It counts for the wind, right? So if you're going to shoot at a target, say, you know, 100 meters away, you may aim left or right of the target depending on the wind direction. So, you know, if you want to hit the bullseye in yellow there, you may aim where that X is when the wind is blowing from left to right. So that's why they call it windage. And then the Kentucky part, again, comes from the rifle. So why would you need to use it? I've already kind of mentioned it, but it's really the final piece of the puzzle when it comes to getting parts warp free. So we have to meet tolerance requirements. You know, maybe we can't change the material. All of our gating and cooling options have been tried. We can't process out the warpage. And maybe we've tried some part design modifications that haven't worked. And we've exhausted all of these things. We still can't get it back to flat. So what do we do? And this is the final piece of the puzzle. So, you know, windage traditionally was done more trial and error, right? You try something that failed, so you try again, and you go through this endless loop of trying again and failing until you finally get it right. So this is a very expensive and time-consuming proposition, and that's a great reason to use simulation, not just for windage, but in you know, anything plastics injection molding related. Avoiding problem avoidance is a better situation to be in than you know, when you have a problem at the press and you have to try to fix it after the fact. So traditionally, you know, the process looks something like this. You design a part, you get everything the way you want it. So you hand it off to the mold maker. The mold maker starts machining. You know, they design the mold, they machine it, they build it, send it to tryout, mold some parts, inspect them, and we find that we're out of tolerance. So now we got to go back to the drawing board, right? Back to design. Maybe we weld up some areas of the mold for windage, remachine things, what have you, and we go through this loop time and time again. And the more loops that are required, the more time and the more money that's going to cost. Seems obvious. So we want to insert the analysis portion of this into that first loop, right? If we get into this design phase, we're going to analyze it, and we're going to see what we're up against before we get into even cutting the first chips on the mold itself. So this is where we want to insert ourselves to make the best use of the analysis. So, you know, cost savings breakdown, you got to justify this. It's got to be worth our while to do analysis compared to doing the traditional windage approach, which is all these tuning loops. So using that oil pan as an example, the one that we showed in that first graphic, this is a typical traditional windage loop. So you might go through, and for this one, sometimes it's upwards of 10, 11 loops, but they're used to budgeting something on the order of 100 over $100,000 to do the tuning loops on something like that. And you can see the amount of time required to do those tuning loops as well. You know, you're a couple months out before you you know, start getting things right. Whereas with the Moldflow windage approach, you know, we're going to do a traditional Moldflow analysis, might be 1 to 2 weeks at a cost of $5,000, you know, depending on the part. We do windage and CAD morphing within a week, and there might be one tuning loop after the tryout, and that's the most expensive part of it. So it seems obvious based on these numbers, and these are, you know, average numbers, we'll call them. Seems obvious that using Moldflow is a good way to approach this. So if we're going to do this, when's the best time to start? As is the case with everything Moldflow, starting simulation early during design phase is the best time to do it, right? When we're in design phase, part design phase, not mold design, part design phase, we have a lot more options at our disposal. We can even try the part design fix before we get into windage, but we need to start simulation early to see what we're up against. And after all those simulation options have been exhausted, and we still have warpage, that's the time to start thinking about windage. So it's okay to do it early, because even if we don't have a full mold design at that point, the windage factor that we would come up with is likely to be similar for the final design once we do have, you know, the final runners, manifold, cooling, etc. in there. So finalize the tooling early and get that all in there, and then determine the windage factor. But I can't stress this enough that you know, even though you're doing some windage analysis early on before we have a final tool design, the final windage shape has to be done with the final tool design. Cooling, you know, gate shapes, sizes, final locations, manifold bore sizes, all of those things are going to play into how the processing works out, and you know, the final shape, you know, the final nitty-gritty detail of how much this is going to warp and in which areas needs to be taken into consideration. So we have to have the final tool design in there. Okay, so then the question becomes, you know, who's responsible for this? Who's going to do the CAD morphing, for example? And you know, we've been doing windage analysis for on the order of 15 years now, but the question always became, who's gonna morph the CAD, right? So traditionally, the molders and the mold makers would take care of that responsibility. You know, if we weren't using Moldflow, they'd use the trial and error methods for creating a windage. You know, for putting windage in the mold. And as we already said, it's expensive and time consuming. And those tended to be more spot corrections, right? Maybe just on the parting line or so forth. But now when we do it through simulation, you know, the expert Moldflow analysts are going to handle the analysis part of it. And the CAD morphing part of it is done with experienced folks with lots of tooling background, right? So the marriage between the Moldflow analysts and the folks with the experience to morph a part, twist it and turn it, but consider all the tooling aspects of the part design. That's the best combination. So we are now doing that in-house. We've been doing it for several years now, and that's great because we have a direct line of communication between the analyst and the person doing the morphing of the CAD. So what are the main steps to a successful windage project? So first thing we're going to do is make sure the part is feesed, and I'll go through each of these individual items here one by one in more detail. But first we need to make sure the part is feesed. We're going to eliminate as much warpage as we possibly can through traditional means. We're going to determine the windage factor, and along with that, determine a shrinkage factor. We're going to morph the CAD and then perform windage checks. So step one is making sure the part is feased. So feasibility study, or DFM, design for manufacturing, assures several things, right? We got to make sure the part is good for tooling. Doesn't make sense to do all this analysis work if we've designed a part that can't even be tooled. We need to make sure we have sufficient sidewall draft. We need to make sure we have good rib to wall ratios, proper fit and function. Basic die draw and die pull directions need to be identified. Again, all these things go into making sure we just have, sound part design and a part design that is feasible for tooling. And a lot of glaring design mistakes can be identified in this step as well. So get that out of the way before we even get to the Moldflow side of things. Once we're there and we're doing Moldflow analysis, we're going to eliminate as much warpage as possible. And I've addressed this, how to do this in other webinars in the past, but just as a refresher, we're going to dip into 5 areas, right? Mold design, gating, cooling, things like that. Part design, material, process settings, and of course our simulation expertise. What kinds of design changes do we need to make? Where among these other 4 areas do we need to dip into most to reduce the warpage as much as we can? So part modification, material, etc. So here's an example, where we dipped into the mold design. This is a 1+1 family mold, that 2 parts that come together to make a fan shroud. And traditionally, the larger of these 2 was made using 3 gates on the larger of the parts. And because it's a fiber-filled material, we decided to go against that and just do 1 gate so we could make the fiber orientation a little more uniform. And that helped us reduce the amount of warpage in these legs here quite a bit, actually, compared to a 3-gate design, so that there wouldn't need to be as much windage put into that. And you can see the expected warped shape of that part. So there's a fair amount of warpage, 4 millimeters vertically, and then you can see the legs of each of these parts coming inward as well in the Y direction. So we did as much as we could to get as much warp out as we could in the traditional sense. And then we started morphing the CAD in Moldflow, not the CAD, but morphing the Moldflow model in the opposite direction to find out how much windage we needed to put in there. So here's our intended position, and then here's our starting position when we reverse biased the part to see how much windage we needed to put in there. So you can see what we're looking for is when we run the analysis, that when it warps, it comes back to the intended position. Okay, and once we have that appropriate windage factor dialed in, then we're good to go. Okay, so the windage model warps back to the nominal. So this is all in analysis, all in Moldflow world right at this point. That's the windage check. Okay, so now we have to, that's part of determining the windage factor. So we will use the final mold design. We got to get the manifold, the runner and gate in there, cooling lines, any cooling inserts. Obviously, we need to make sure we have good material data and get our process settings dialed in to determine that windage factor. Another way to look at a windage check is to kind of do overlays. So we're gonna take this model, we're gonna predict the warpage, and then we're gonna export it in its opposite direction. And our starting point is going to be a scale factor of 1. Okay, so we take this warp shape and warp it in the opposite direction. And this is what this looks like in Moldflow. So you see the Moldflow meshes here overlaid with one another. In the blue, we have the nominal geometry. That's where we want things to end up. When we ran that first analysis with the final tool design in there, we have the predicted warp shape in green, right? So it's going to shrink and it's going to warp. So 2 things happening there, and you see it getting smaller and you see it warping inward as well in the green there. So we take that, and like I said, we put this in the opposite direction, and that opposite direction mesh is what we see in yellow here. Okay, so it's bigger, which is what we would do normally, right? We would expand the part to account for shrinkage, but it's also warped downward, so that, it wants to warp inward and shrink inward simultaneously. So we have those two effects going on, and it's being accounted for in the biased shape, the outward bias shape in yellow there. Okay, so when we did that and we ran that analysis, that windage check analysis, it warped back as you see here. So we have an overlay of the two meshes, the nominal in blue, and the red is where it came back to after we ran the windage model. So if you pick some critical points around the periphery here and take some measurements as to how they came back, you can get a pretty good sense of how close you are with the windage factor you chose. In this case, it was 1-to-1. Sometimes it's going to be something less than that. Sometimes even it might be a little bit more than that. But we have to do this windage check and do this overlay to see what the how close we can expect to be. Okay. Keep in mind though, we're still in Moldflow world right now. We haven't done anything with the CAD yet. Okay. Another way to do it is to use overlay programs like inspection programs. When you do 3D scans of parts, you can overlay the Moldflow mesh from the windage check model with the intended shape and see how close you are in all these different areas of the part. So everything comes out close to 0, you've dialed in the right windage factor. But is the windage factor always going to be 1-to-1? Not always. It's I'd say most of the time that's about where we are, but many times we're something less than that. And the reason is this, and I put the graphic of this nice archway here up for effect. Our original starting point in Moldflow is essentially a flat part, our intended shape. But when we morph it back to the opposite of the warped shape, oftentimes we're creating an arc in the part. And as we know from architecture, an arc shape is stiffer than a flat shape. So it wants to resist that warpage that we predicted, and it might come short of where we want it to be, the intended shape. So it's not uncommon to see windage factors be in the 0.8, 0.9 area. It's not that common, but it is common enough to where we have to do this check to make sure that we don't just expect it to be a 1-to-1. Along with the shape of the part, we have to determine the right size of the part, and we have to use a lot of different sources to do that. We have Moldflow results where it will give you shrinkage factors, and these are linear shrinkage factors in 3 directions. We have the Moldflow material deck, so well-characterized materials will come with a lot of a wealth of shrinkage information. And this is shrinkage information that is generated over a lot of different conditions, different sets of process conditions, different wall thicknesses, and so forth. Material directions, fiber. If it's a fiber-filled material, there's different shrinkage and different direction based on fiber orientation, molecular orientation for unfilled materials, etc. So well-characterized materials in Moldflow will give different shrinkage values for different conditions. We also have, of course, the material supplier to rely on for their published shrinkage data. And then, of course, we have our experiences from molded samples. But the reason this becomes important is because materials don't necessarily shrink uniform, or parts don't shrink uniformly across the mold, right? So in this case, you can see we got shrinkage in one direction dialing in at around 11 thousandths per inch, and in the other direction it's dialing in about 5.5 thousandths per inch, right? And you can see this, and we talk linear shrinkage values when we talk mold steel. But in analysis, we often talk in terms of what we call volumetric shrinkage numbers. And you can see how shrinkage plays out in different areas of the part. You see this thick disc in the middle here exhibiting a lot higher shrinkage level than many of the other areas of the part. So when we, talk about part design, we talk about processing, we talk about where we put our gates, all of those things factor into which areas of the part shrink more than others, because you cannot get a perfectly uniform shrinkage across the part. You just can't. It's impossible. And unfortunately, that's what we have to assume. That's what mold makers have to assume when they build a tool, right? They have to expand the nominal shape by some shrinkage value and assume that it's essentially uniform shrinkage across the part. Now, in some cases, mold makers will cut different numbers in different directions, but even then, pick a direction, X direction, for example, you're not going to get perfectly uniform shrinkage across the span of the part in the X direction. So we have to pick a number for each of the three directions. And again, we're going to use all these sources to help us do that. And you can see in this case, right, we've got a gate here. This is a fiber filled material. The predominant direction of those fibers is across the part in the direction of flow. And then when we go down the leg of the part here, it's going to be downward for the most part in that leg. So we're going to have different shrinkage values in different directions, and that's exactly what showed up here when we picked different directions to measure that shrinkage. Okay, so there's another area of Moldflow that we can look, and it'll give you composite shrinkage values in each of the three directions, and you can see how that played out here in X, Y, and Z. Okay, so a lot of different ways we have to do this, but the big point here is that we have to pay attention to that, because we have to have a starting point when we get into the CAD morphing. We also have to pay attention to material data. Good material data, I've hammered on this thousands of times before, is essential to good Moldflow analysis. But nowhere is it more essential to analysis than when you get into windage, because windage is that extra step, right? We're trying to dial this in, and the less you pay attention to shrinkage or material data rather, the more that error propagates throughout your part. And when you get into windage, too many accumulated errors is going to do you in. So this was a case where we were fortunate. We had molded parts already, and they were building a new tool. So we looked at it and did some baseline studies, some correlation work, and found that the material data we had was old and incorrect, and it predicted way too much shrink. And you can see how that manifested itself in terms of the warpage values here. We've got almost 3 times the amount of warp in the one on the left versus the one on the right. So the material data was regenerated, and we got things right in that case. So we were able to use that new material data to generate a much better windage file from that. So when we ended up doing the windage on that, we came up with really nice flat parts on that. Okay, so we're at that stage now where we know the windage factor. We know how much shrinkage we want to apply in the different directions for the mold. Now we actually have to make a file that the mold maker can use to cut steel. So that's where the CAD morphing, and this can be the touchiest area of windage. So we're going to take something out of Moldflow, either in STL or step format, and that file is going to have the proper windage factor in it. And we're going to expand that file, or expand the nominal CAD file with the proper shrinkage factors that we just discussed on the previous slides. We're going to protect features for die draw. That's important, right? We can't have any die lock conditions. And we're going to morph to match that windage shape that we had in this STL or step file. Okay. So it's not going to be a perfect match to the STL or step file, because we have to protect these features for die draw, and also because that Moldflow model is going to have all those different, millions of different shrinkage factors all across the part, in their exact locations. right? We're not going to put all those individual little shrinkage into our morph CAD model. We're going to apply, more averages across each of the 3 directions, X, Y, and Z. So here's the example over here. So in yellow, we have the nominal. That's where we want things to end up. Purple, we have the windage file. We had to twist this thing 15 millimeters. So what do we mean by protecting for die draw, right? So let's say we have a rib designed into the part, and you can see in this file right here, right, millions of ribs. So that was quite the undertaking to keep all these ribs in die draw. But let's focus on one rib here on a flat part, up and down, have a little bit of draft on it. And now in our windage model, we've got the deck of this part starting to slant in one direction, and the rib goes along with it. Well, now all of a sudden we've got this area right here in danger, right? We've got die lock condition. We can't have that. So we can do one of 2 things. We can correct the rib draft, which is okay. There's a lot of work in that, and you can run into 2 problems with that. You could have a thicker base, which opens you up to more sink, the potential for sink, or you can draft in the other direction and make the tip of the rib thinner, which might open you up to issues with filling that rib out. So I don't really like going in that direction. You can do it. It's a little bit more work, obviously, with CAD modeling as well, but that's not a preferred way. But just to illustrate the point, that's what we have to do, is we essentially have to remove that die lock condition. So another option is to leave the features in die draw. So this is still straight up and down, but the wall that it attached to has been morphed into the windage shape. That's our preferred way. And sometimes you can get into situations where, when this warps back to flat, right? So then that might leave a little bit of a slant in the rib. So we have to make sure that we're paying attention to the fit and function of those features when we're doing this. Here's what it looks like on a 3D mesh. So again, we're going to morph within the die draw and die pull directions. In the blue here, we have the final morph data. The Moldflow windage shows that this leg is, cocked to the side quite a bit. So we had to stand that one straight up to match it better. And again, we're going to focus on the fit and function in the critical areas. Things like bosses, locating features, ribs, trim edges, overall sizes, things like that. Some critical areas, we may leave stock safe. In other words, we want to be double, triple sure that, things like locating features or whatever, we have a little bit of leeway to dial those in a little bit more precisely in the end. So we'll leave those stock safe to be able to do that, to have the freedom to do that at the end. And of course, throughout the morphing, we're going to be doing draft analysis checks. So that's a 3D mesh. We're big proponents of using midplane models here at CAE Services. We feel like those, in the right situations, give us the most accurate warpage results. And of course, the most accurate warpage results are necessary to get the best windage models. So we have to make sure we have CRIMS data. I won't go into detail, but that is the shrinkage data I was referring to earlier. CRIMS data gives us all of that shrinkage information over a wide range of different process settings and so forth. So we overlay the midplane model with the midplane windage model with the CAD, and we start tweaking surfaces until we match that as best we can. Again, within keeping features and die draw and fit and function and all that. So it's never going to match up perfectly to the windage model in Moldflow, but it doesn't necessarily need to. So after we morph the CAD, now we got to go back to Moldflow. right? We have now a different shape in our CAD than what we used from Moldflow, because we've protected for die draw and all that, and we have to see what those effects are on the final shape. So we're going to rerun using all the same conditions, gating, runners, cooling, process settings, and so forth. And we're going to compare the results of that to the nominal shape to see if we're still okay. So in some cases, protecting for die draw is going to change our part pretty significantly, especially, the more ribbing we have, the more that tends to become necessary. So we're going to adjust things, tweak them until we get that windage check to pan out for us. So this is a look at what, a comparison of the two windage check models, right? This is what you saw earlier. So this was all done in Moldflow world. This is the result of the windage model and the final windage check of that morphed CAD model. And you can see there's some numbers that are a little bit more out than they were previously, but they're still within tolerance. Here's what it looks like when you use an overlay program. And you can see actually in this case, there was a slide that forms this, and they decided not to want to modify that slide with windage as well. That was going to cause some additional time and money to do that. So they were okay with these still coming in. So that's why those two sides did not check out after we scanned parts and overlaid them with the nominal. But the rest of the part came in pretty darn tight. And then again, back to this. So once we created the CAD model, the windage CAD model, remeshed it in Moldflow, we still got to check to make sure things come back to the nominal position. So after all said and done, enjoy the results. In this case, we had two major conditions of perpendicularity of this boss and of this L shape. So measured parts on a CMM in this case, perpendicularity of the boss, all well within tolerance. Here's a couple other examples. 10 millimeters of windage, the windage model's in blue. You see the separation between the nominal and the windage model. This was a case where we put 13 millimeters of windage in the purple model there, and then our tooling engineer attended this tryout and said it came out bang on in the mold tryout. So just some basic examples of what's possible. Very complex parts, parts with a fair amount of windage to put them in them, even though the geometry itself is relatively simple. So all kinds of different parts. So the next part is the fun part, right? We got to manage expectations, the difference between perfection and predictive. And this isn't just windage, it's everything Moldflow. The expectation should not really be 100% perfection. The expectation in this case should be the reduction of tuning loops. Ultimately, you're going to get to a flatter part. The question is how fast you're going to do it and how much time and money you're going to spend to do it, right? Windage should be considered when other options aren't possible. We went through that list earlier. And I would argue that there's no better way to do this than through the use of Moldflow. But you got to make sure you're doing everything right? You shouldn't enter into windage lightly when you're using Moldflow to do it, because of what I said earlier. Those errors, any error in any of the variables that we deal with in Moldflow, and there's a million of them, any uncertainty in any of those compound, right? It's a snowball effect. You introduce error into the process, the material properties, the tool design, the part design, any of those areas where there's uncertainty, those are going to compound. So got to make sure we're doing it the right way. This particular part, by the way, I said there was 15 millimeters of twist in it. Came out dead flat around the periphery of the bottom of the part here. There was still one tuning loop that was required, and this is where protecting for those features, you know, being stock safe, came in handy. So some of these mounting bosses needed to be dialed in laterally with one more tuning loop. So, but heck of a lot better than going through 10 or 11 of them. And I mentioned the Moldflow expertise. So the expertise is going to help us know when the results are reasonable, whether it's material data, the mesh, you know, the know-how of moving gates or improving cooling, you know, how to process to fix aesthetics or warpage, you know, how to use part design to help fix warpage, how to use windage to fix warpage. So all of these things come into play. We want to try to avoid windage as much as we can, but once we get to that point, we better make sure we're minding our P's and Q's when we're doing our analysis work. Okay, so that's the windage aspect of things. In a minute, we're going to open up the phones here, so to speak, to the field to allow you to ask questions. It'll be a live question and answer session. But in the meantime, let's talk about what's happening here at CAE. You know, I talked about the Autodesk partnership. We've been Autodesk partners for going on 5 years now. So we're tasked with software sales, Moldflow software sales, training and mentoring. I'm our lead trainer when it comes to learning the software. If you want to learn more about Moldflow itself, you know, we can always schedule a day to spend some time demoing the software. From a learning aspect, you know, we're building expert analysts. That's our motto here. So we have a classroom and online training. We have our Ask the Moldflow Experts webinar series, which is what you're watching right now. So look for the ones in the future in your email or online, or go to our website, what have you. If you ever want to spend some concentrated time talking about Moldflow, whatever the topic may be, you pick the topic, and you know, I will be able to, you know, just go through whatever that topic is with you on a one-to-one basis. So Moldflow office hours is what you would do there. So feel free to sign up for that. We're also now doing mold steel structural analysis. That's kind of a new offering we have. You get into these situations where you have like a tall core and lots of pressure pushing on it, and after so many cycles that you get a crack in the tool. So that's always a bad deal, right? So doing steel structural analysis is an important thing. That's our website again, so you can go visit the website and see what we're all about. And of course, you can follow us on LinkedIn as well. Okay, so let's have a little Q&A here. I am going to attempt to unmute everybody. In the question, or in your control box, or whatever you want to call it, for the GoToWebinar, you can raise your hand. So when you raise your hand, I'll look at it. So first come, first serve, and I will unmute your mic and let you ask the question out loud. Looks like Bosco has a question. Bosco, go ahead. Bosco, you there?
Sorry. Hi. Sorry. I'm using a Bosco account. This is actually Taka from Markdown Engineering.
Okay.
Okay. Yeah. So I have a question about shrinkage. In the Moldflow result, we usually get X, Y, Z axis, and then we get a shrinkage percent to these three axes. But in tooling, we have to apply one shrinkage. I was just wondering if there's any like specific or correct ways to take the average from these three axes.
Well, the first thing you have to do is see how different those numbers are, right? If those numbers are wildly different, then that should throw up a red flag to start thinking about cutting different values into your steel in X, Y, and Z. And then you got to be careful of the composite numbers that Moldflow spits out. I I like to pick point pairs, in Moldflow and see how much actual shrinkage there is in between 2 points, but the point pairs can't be necessarily spanning the whole part, because it's only going to show you a percentage difference between in the distances between those 2 points, which isn't necessarily shrinkage. Some of that might be warpage. So we got to be careful how we use those numbers, and that's where that the expertise comes in. So picking point pairs is a good way to do it. And again, I don't want you to just necessarily just use Moldflow data. Temper that with what, there's a lot of good experience out there from the material supplier, from the molders, et cetera. So we gotta dial into all that as well. Does that make sense?
Yeah, thanks so much.
Sure. Okay, Phil has a question. Give me a second to unmute you here, Phil.
Hey, Tim,
right.
Thanks for taking my question. Tim, I've got a customer that's asking questions about adding D3 juncture loss or pressure-dependent viscosity to our material card. Could you talk about that a little bit, about the utility of it, or just share with me your significant knowledge? Thank you.
Yeah, absolutely. So what Phil is asking is a materials question. So when we do Moldflow analysis, we rely on the material properties, and there's several different material properties that go into any analysis. So in the filling stage and in the packing phase, of course, for filling, we have to know what the viscosity of the material is. And if we do a good job of characterizing the viscosity, then presumably we do a good job of determining how much pressure is required to fill that mold. Another part of that pressure equation are the two things that Phil just mentioned, juncture loss and D3. For juncture loss, that covers additional pressure losses when we have a lot of different size changes in the feed system, runners, gates, etc. Okay, so just moving material from point A to B, if there's some distance between point A and B, there's a pressure loss associated with that. That's the viscosity data. But to get across a juncture from one size diameter to another, that's a whole different ballgame. That's called juncture loss. So essentially, you're moving 0 inches to get across that juncture, but there's a pressure loss associated with that. So that's where juncture loss data comes in. And if you have a complicated manifold system, for example, that juncture loss calculation can become significant. So you want to make sure you get the right pressure drop calculation prediction through the runner system. And then the third thing that the other thing that Phil asked about was the D3 coefficient. So D3 is part of the viscosity calculation, and it becomes important when the pressures start to climb into the higher realms of typical pressure. So once you start getting up above about 15,000 psi, the viscosity actually starts to be dependent upon what pressure you're at. Okay, so this happens a lot with amorphous materials in particular. Polycarbonate's a big one, PCABS, and there's some history behind the Moldflow material database. There's I don't even know the number right now. It's something on the order of 12,000 materials in the Moldflow database, and a lot of the materials were initially characterized decades ago. Even before the juncture loss and D3 coefficients were really even included or thought about much in Moldflow circles. So, they've kind of hung on and stayed in the database, but again, you have to know what you're looking at when you look at a material deck to know whether or not you might be under predicting pressures when you're using that material. So a lot of the materials nowadays are, it's kind of standard to get those things tested, but not always. So you gotta know if you've got it or not. The consequence of all this is if you predict your pressures improperly, then the amount of pressure that the part cavity itself sees is going to be wrong. And if it's seeing the wrong amount of pressure, it's not going to be packing out. It's not going to be predicting how the part's packing correctly. So If that's wrong, then your shrinkage values are wrong. If your shrinkage values are wrong, your warpage values are wrong. If your warpage values are wrong, then you can't expect to do a very good job of windage. So it all, again, it's that snowball effect, and a lot of it starts with that material data. So good question, Phil. Those are the material properties that can often sink a project if you don't have them. Okay, looks like I don't know what order this came in, but I'm going to take the one on the top here. So Chris Ford, you have a question?
Yes, can you hear me?
Yep.
In the beginning, in the early part of your the webinar, you said that sometimes that more gates or less gates, especially with a fiber material, doesn't really have the effect on shrinkage. I mean, there's really not an advantage of putting additional gates or drops. Is that predominantly towards like a glass filled material or a mineral filled material, or is
It can
that?
be. And every situation is different, but more gates. So there's two effects, right? Well, really three primary effects that contribute to warpage. And I've covered this a little bit in other webinars, but of course you have cooling. That's a separate issue from what we're talking about right now. But
Right.
then you have packing and you have fiber orientation. So materials shrink for different reasons, right? So from just bulk packing, you're jamming more material in there to compensate for shrinkage. That's what I call bulk packing, right? So areas closer to the gate, generally you're going to pack better than areas that are farthest from the gate. Areas that are thicker are going to shrink a bit more than areas that are thinner. Areas that are hotter are going to shrink more than areas that are cooler, right? So those are kind of the bulk packing effects from the packing phase of injection molding. But you also have shrinkage differences that are set up because of fiber orientation in a glass fiber filled material. Those shrinkage differences tend to be dominant when you have a glass filled material, and you have a pretty large disparity between the in fiber shrinkage direction, the fiber direction shrinkage versus the transverse shrinkage. And those shrinkage differences can sometimes be on the order of 10, 12 to 1. And
Wow.
and that shrinkage variation can really set up for a lot of warpage. But for unfilled materials, you also have molecular orientation. So that material freezes at the surface, and the direction of flow, in the direction of flow, you often tend to have actually less shrinkage than transverse to flow. The differences tend to be fairly minor, but they are there, and sometimes those can actually play an effect too. So it really is just a case by case basis. And in the example I gave there, the fiber orientation was the dominant cause. So we had a bunch of different fibers going a lot of different directions, and it was harder to control the shrinkage. And sometimes you get kind of this wavy pattern because of you have like this semicircular fiber orientation effect coming out of your gate, and that can set up kind of a wavy pattern along edges, and that's harder to control for windage. So we made a decision in that case to go with a single gate so that we can control the fiber orientation along that inner diameter, that fan shroud, a lot easier.
Okay.
So but you have to there's a downside to that, right? One gate. Now we had to balance the runner system. Now we had to deal with a little bit more pressure to fill the part, but it wasn't so egregious that decision was a bad one. So
Right.
that was the reason for the why we did that one that way.
Is it possible to get a copy of this presentation that you presented?
There will be a recording. Nick Lorenzana, who is our inside sales person here, you'll be getting a follow-up email, I believe, after the webinar. So.
All right, perfect. Thank you.
Okay. Yep, no problem. Thanks for the question. Marshall, you've got your hand up.
Yeah. Can you hear me?
There you are. Yep, I got you. Go ahead.
So I'm still a little unclear on how you actually determine the proper windage factor. I know you mentioned warping the shape in the opposite direction and using overlays, but I'm curious if you can do that in Moldflow Advisor or if you can only do that in Insight.
Yeah, you can't do that in Advisor. Advisor does not have the ability to output a warped shape in the opposite direction. So yeah, this is all Moldflow Insight generated. And yeah, be careful with Moldflow Advisor. Moldflow Advisor is a great product, but it's intended really for kind of, hey, can we mold this part and what can we expect directionally, so to speak. But when we start getting into nitty-gritty detail of numbers, you know, absolute values of numbers, just be careful with the Advisor results when you're looking at that. Okay.
Okay, thanks.
Yep. Okay. I think that is about it. Anybody else? Okay, well, I think that about covers it. Again, you should be seeing an email, a follow-up email after the webinar. If you have more questions, feel free to give me a call or send me an email. Put those on the screen there, so feel free to take a screenshot of that or whatever. But appreciate everybody taking time out of your day to watch the webinar. Look for you know, future webinars in your emails and online and so forth. We'll do them monthly and new content about every other month, but repeat content on a monthly basis for sure. So enjoy your day and get out there and do some windage analysis. It'll save your life in some cases. I'm confident. So give us a call if you have questions, and appreciate you attending. Thanks again.